Hello everyone, welcome to this lecture. The plan for this lecture is as follows. In this lecture we will introduce linear congruences and we will see two methods for solving linear congruences, one using extended Euclid's algorithm and another one the famous Chinese another one due to the famous Chinese remainder theorem or CRT. So, let us start with linear congruences. So, in regular algebra you often come across linear equations of the forms a times x equal to b. That means, you are given some real numbers a and b and you have to find out the value of this unknown variable x such that this condition is satisfied. And how do we find out the solution for the above equation? By solution of the above equation I mean to find out the value of this unknown x, and if we know that the value of a is not 0, then I can say that if you multiply both the sides by 1 over a and 1 over a is considered as the inverse of a in your regular algebra, then I say that x is equal to b over a. So, that is the solution for your linear equation here. Okay. Now, when I say linear congruence, we are more or less in the same situation except that we are in the modular world. That means, everything is given modulo sum modulus. Okay. So, we will be given some a and b and a modulus n, and our goal will be to find out x such that a times x is congruent to b modulo n. That means, a x when divided by n and b when divided by n gives the same remainder. You have to find out the value of x, or equivalently a x minus b is completely divisible by n. Okay. So, for instance, if I say that I am given 6 x congruent to 4 modulo 10 and if I want to find out the value of x, then the possible solutions are x equal to 4, because if x is equal to 4 then you get 24 congruent to 4 modulo 10, which is true because 24 minus 4 is completely divisible by 10. If you substitute x equal to 9, then you get 54 congruent to 4 modulo 10, which is again true because 54 minus 4 is 50, which is completely divisible by 10. And it is not the case that these are the only solutions. You have infinite number of solutions. That means, any number of the form 4 plus 10 k, where k can be either positive or negative, will also satisfy this linear congruence. In the same way, every number of the form 9 plus 10 k, where k can be either positive or negative, will also be a solution of this linear congruence. So, that is an interesting thing. Unlike regular algebra where the solution was just b over a, of course, you can also say 2 times b over 2 times a is also a solution, 3 times b over 3 times a is also a solution, right, but more or less their primitive form is b over a. In the same way, the primitive solutions, primitive in the sense the base solutions are 4 and 9, and now you can create infinite number of solutions out of these two solutions by adding all multiples of 10. Okay. So, now let us see how we can solve linear congruences using extended Euclid's algorithm. That is our method number 1. So, you are given a, b and n, goal is to find out this unknown x. Now, as we did for our equation in the linear algebra where we said that divide both the sides by a provided a is not 0, the question is, can we do something similar in the modular world as well? That means, can we say divide both the sides by a, and divide both the sides by a, by that I mean multiplying both the sides by multiplicative inverse of a, and that is possible only if GCD of a and n is 1. So, remember in the last lecture we proved that the multiplicative inverse modulo n exists only if the number for which you want to find out the inverse is co-prime to your modulus. So, if your number a is co-prime to your modulus n, then I know that a inverse exists, and hence I can say that divide multiply both the sides by the multiplicative inverse, right. So, that is the method of solving linear congruence under this restricted condition. So, if your GCD of a and n is 1, then by running the extended Euclid's algorithm, compute the multiplicative inverse of a, okay, namely b, I can stress this A inverse is not 1 over A in the modular wall, it is an integer. And now I multiply both the sides of this linear congruence by this A inverse. So, I will get this linear congruence, and I know that A into A inverse is 1 modulo n and 1 into x modulo n is x. So, I get that x is congruent to B A inverse modulo n. That means, I can say that the value of x being this plus any multiple of n is a solution for this linear congruence. Okay. Because all these values of x minus this value B A inverse is completely divisible by n. Okay. However, this method will work only if your number A is co-prime to your modulus n. What if the number A is not co-prime to your modulus n, then we have to follow a slightly different approach, which is complicated, and I am not going to discuss that method. Instead, I will discuss another way of solving linear congruences, in fact, a set of linear congruences, and this method is often called as the Chinese remainder theorem, attributed to the ancient Chinese, but it is also believed that the ancient Indian mathematicians also used the same technique for solving a system of linear congruences. So, what exactly we mean by system of linear congruences? So, very often you come across a puzzle of the following form. You have an unknown number x which is not given to you, but it is given to you that that unknown number x has the property that when it is divided by 3, it gives you the remainder 2, when divided by 5, it gives you the remainder 3, and say when it is divided by 7, it gives you the remainder 2. Under this condition, find out the value of x. Of course, again you can find out infinite number of x satisfying this condition, but what the CRT method says is it gives you at least one x which satisfies this condition, and then from that you can find out the other values of x as well. So, the above puzzle, the above instance of the puzzle can be formulated as a system of linear congruences, namely my goal is to find out an unknown x satisfying the linear congruence that it is congruent to 2 modulo 3, it is congruent to 3 modulo 5, and it is congruent to 2 modulo 7. And the special property of this problem instance is that you are given the value of x modulo various modulus. Those individual modulus are pairwise co-prime, right. So, let me now formally state the theorem statement of Chinese remainder theorem, and then we will prove it. So, you are given n different modulus which are pairwise relatively prime. That means, you take any pair of modulus mi and mj, they are co-prime to each other, and you are given n number of remainders a1 to an. So, you have to find out an unknown x which is congruent to a1 modulo the first modulus, it is congruent to a2 modulo the second modulus, it is congruent to an modulo the last modulus. Now, what is the Chinese remainder theorem? It says that this system of n linear congruence has a unique solution modulo the bigger modulus. And what is the bigger modulus? It is defined to be the product of n modulus. Okay. So, in other terms, in other words, what does it mean unique solution? By unique solution, I mean that there is only one value of x in the range 0 to m which satisfies simultaneously all the n linear congruences. But that does not mean there is only one solution. There is only one solution in this range, but there can be other solutions as well outside this range. In fact, there are other infinite number of solutions, and what you can say about the other solutions, they are obtained by adding various multiples of m, namely they are congruent to modulo m to this solution x which is in the range 0 to m. Okay. So, we now want to prove the Chinese remainder theorem, and there are multiple things which we have to prove. The proof strategy is as follows. We will give the construction of one of the solutions. Okay. in the range 0 to m minus 1, but that does not mean that that is a unique solution. Remember, there are two parts of the proof. We have to show that there is at least one solution in the range 0 to m minus 1, which we will be doing in this lecture, and then we also need to show that that is the only solution. You can't have any other solution in the range 0 to m minus 1. Okay. That we will do in the next lecture. By the way, when I say unique solution, again and again I am stressing unique solution modulo m, that means unique solution in this range. Outside this range you can, so if x is a solution, any number of the form x plus L times m, where L is positive negative, will also be a solution of this system of linear congruences, but these values, these solutions will be outside the range of 0 to m minus 1. So, do not get confused in this term unique solution. So, now let us see how exactly we can find at least one solution, that will be the goal of this lecture. So, the construction idea of that solution will be as follows. We will try to find out a special linear combination of the n remainders that are given to us. So, remember we are given n remainders a 1 to a n. We will try to express that unknown x which we want to find out as a special linear combination of these n remainders, namely we will try to find out the special linear combiners C 1, C 2, C n. These linear combiners will be special in the sense that if you take the ith combiner C I and reduce it modulo m I, namely the ith modulus, you will get 1, but if you take the jth combiner and try to reduce it modulo any other modulus, you will get 0. So, for instance, what I am saying is that my combiner C 1 will be such that C 1 modulo m 1 will be 1, but the same linear combiner C 1 modulo any other modulus will be 0, namely the n other modulus, n minus 1 other modulus. All this will be 0. In the same way, your C 2 modulo m 2 will be 1, but C 2 modulo m 1, C 2 modulo m 3, C 2 modulo m 4, C 2 modulo m n will be 0. So, that will be the property of the special linear combiners. How exactly we find them, that is a whole process, but imagine for the moment that it is possible to find out these linear combiners. Okay, that means I know how to find out these linear combiners such that x is indeed equal to this. Now, you can see that if I take this value, once I have found C 1, C 2, C n, then I will have this exact value. Then if I take this RHS and compute RHS modulo m 1, then that will be same as a 1 modulo m 1, because for all other summents I will be getting C 2 modulo m 1, C 3 modulo m 1, C n modulo m 1, and their effect will be 0 0 0 0 0. It will be only C 1 times a 1 modulo m 1, and C 1 modulo m 1 is 1, because that will be the property for my linear combiner, and hence this value of x that I have obtained modulo m 1 will be indeed a 1. In the same way, assuming that I have found C 1, C 2, C n satisfying these conditions, what I can say about the x that I have obtained modulo a 2. If I do x modulo a 2, then it will be equivalent to this C 2 times a 2 modulo m 2, because the effect of this term will be 0, the effect of third term will be 0, the effect of the nth term will be 0, and so on. So, that is the idea here. So, everything boils down to how exactly we find this special linear combiner C 1, C 2, C n satisfying these properties. So, let us see how we find them. So, remember my bigger modulus m is the product of all n modulus. Now, I define n number of small sum modulus. So, my first sum modulus m 1 is the product of all the n modulus except the first, namely m 1. My m 2 is the product of all the n modulus except m 2 and so on. So, in general the sum modulus m k is the product of all the n modulus except the kth modulus, right. Now, my claim is that if I take the modulus small m k and the modulus big M k, then they are co-prime to each other, and this is true for every k from 1 to n. Now, the proof is very simple. Assume that the GCD of small m k and big M k is not 1, right. So, if their GCD is not 1, that means there is another common divisor, and that will have some prime factor as well, right, because every number has a prime factorization. So, that means if the GCD is not 1, then that means there is at least some common prime divisor which divides both small m k and big M k. Now, if this prime number p divides this modulus big M k, then since M k is the product of k n minus 1 number of small modulus, right. So, it is the product of m 1, m 2, m k minus 1, and m k is missing, m k plus 1 up to m n. So, it is the product of n modulus, and I know, and I am assuming here that p is a divisor of m k. Now, p is a divisor of this m k, then it has to either divide m 1, or it has to either divide m 2, or it has to either divide m k minus 1, or it has to divide either m k plus 1 and so on, because if p does not divide any of these small moduluses m 1, m 2, m k minus 1, m k plus 1, m n, then how at the first place it can divide m k, because p is a prime number here. Okay. So, that means it has to divide some small modulus, call it m j, and we already know that p divides m k. Now, this m j is definitely different from m k, because m k, this small m k, is not present in this capital M k, right, it is not present. So, that means now I have obtained a pair of small moduluses m k and m j, which are not co-prime, because p is a common divisor of both m k and m j, which is a contradiction to the fact that the n small moduluses which are given to us, they are pairwise co-prime. Okay. So, that is a proof of this claim. So, I am retaining this claim here. Now, if this small modulus m k is co-prime to this m k, then I can say that I can find out the multiplicative inverse of this big M k modulo small m k, right. So, I am treating small m k as my modulus and big M k as the number. So, I am treating it as my a, and this is my n. I know that this is my a, this is my n, and I have shown that a is co-prime to n, and hence I know that multiplicative inverse of a modulo n exists. So, I know that multiplicative inverse of big M k modulo small m k exists, and I can find it out using the extended Euclid's algorithm. So, let y sub k be the multiplicative inverse of big M k modulo small m k. Okay. That means this property holds, that means you multiply y k with big M k and then you take modulo m k, you will get the remainder 1, you will get the answer 1. Okay. So, these are the various facts here. So, this is my big M k and the corresponding multiplicative inverse is y sub k, and this I can find out for every k in the range 1 to n. Now, my claim is that the product of this y k and big M k modulo every other modulus except the kth modulus is 0. So, for instance, if k is equal to 1, what I am saying is we know that y 1 m 1 is congruent to 1 modulo first modulus, but the claim that I am now making is the following, that y 1 times m 1 will be congruent to 0 modulo every other small modulus. That means, you take the remaining n minus 1 moduluses, y 1 times m 1 will be congruent to 0 modulo those n minus 1 modulus. Okay. Similarly, if you take y 2 times m 2, we know that that is congruent to 1 modulo the second small modulo m 2, but with respect to the first modulo m 1, the third modulo m 3, fourth modulo m 4 and so on, y 2 times m 2 is 0, that is a claim, and the proof is very simple here. So, I know that big M k is the product of n minus 1 small moduluses here, namely it is a product of all the n moduluses except the kth modulus, and hence if I divide this m k by m 1, I will get remainder 0, because this number is completely divisible by m 1. If I divide this big M k by m 2, again it is completely divisible by m 2. If I divide this big M k by m j, again it is completely divisible by m j. If I divide it by m of k minus 1, it is completely divisible. If I divide it by the k plus 1th modulus, again it is completely divisible, right. So, that is a very simple fact here. So, that is the third property that I have retained here. Now, remember the proof strategy was that I want to express my unknown x in terms of as a special linear combination of my remainders a 1 to a n, and my claim is that now I have obtained those special linear combiners. So, my claim is that if I take this linear combination of the n remainders, namely y 1 times m 1 times m a 1. So, this is my first linear combiner, this is my kth linear combiner, and this is my nth linear combiner. My claim is that this value of x is indeed a solution for this system of linear congruences, okay. And you can easily verify that. What will happen if I take the value of this x and compute modulo m k, I compute x modulo m k. So, if I compute x modulo m k, then that will be same as this first summand modulo m k, the second summand modulo m k, the kth summand modulo m k, and the last summand modulo m k, right. Now, what can I say about the first summand modulo m k? So, I know that this property holds. That means, if I take the first summand here, there big M 1 is present, and big M 1 is congruent to 0 modulo m k. That means, big M 1 is completely divisible by my small modulus m k. So, this first summand is completely divisible by m k. So, it will give me the remainder 0. Similarly, the second summand will have big M 2, which is completely divisible by m k. So, that is why the overall second summand is completely divisible by m k, and it will give me the remainder 0. But when I come to the kth summand here, in the kth summand I know that I have y k times m k present, and y k times m k modulo m k is 1. So, that is why this overall term modulo m k will give me a k, and again the remaining other terms will vanish, they will turn out to be 0. So, it will turn, that means it tells me that if I divide x by m k, I will obtain the same remainder that a k gives me on dividing by m k, or equivalently x minus a k is completely divisible by m k. Okay. So, that means by following this process I can find out at least one solution satisfying the whole equation in the sense the whole system of linear congruences. But I want to find out a solution in the range 0 to capital M minus 1, right. How do I obtain that? So, for that again let me reiterate what I am being saying again and again. If you have one solution x satisfying the n linear congruences here, then any number of the form x plus L times your bigger modulus is also a solution for the same system of linear congruences, where L can be positive, negative. That means, okay, let us first prove this claim, and then we will see how exactly we can find out a solution in the range 0 to m minus 1. So, since x is a solution, okay, which satisfies the system of linear congruences, that means x has these properties. That means x is congruent to A1 modulo M1, it is congruent to A2 modulo M2 and so on. Then what can I say about x plus Lm modulo M1? Well, x plus Lm modulo M1 will be same as x times x modulo M1, because this L times m modulo M1 will give you 0, because m is completely divisible by M1, because remember your m is the product of all the n modulus. So, that means even though this might look like a different number, this different number when divided by M1 will give you the same remainder which you obtain by dividing just the value x by M1, and we know that x on divided by M1 will give you the remainder A1. So, that means this satisfies this different number satisfies the first linear congruence. In the same way, the same different number satisfies the second linear congruence and so on. So, now this claim is true, we have proved that. So, assuming you have a solution x satisfying your linear congruence, now if that x is not within the range 0 to m minus 1, then you keep on subtracting multiples of capital M from it. You make it small, because every time you subtract one full multiple of m or one full times m, the new number is still a solution. That means, if x is, what I am saying is that if x does not belong to the range, if x if this condition is not satisfied, say, and you want to find out an x prime which is also a solution and within the range 0 to m, then what I am saying is that you keep on subtracting x. That means, you first compute x minus m and check whether this x minus m is within the range 0 to m or not. If not, then compute x minus 2 m, then compute x minus 3 m, because all of them, these new numbers also will be solution for your system of linear congruences, and eventually by appropriately choosing the value of L, you will obtain an x which will be in the range 0 to m minus 1 and which satisfies all the n linear congruences. So, that shows that using the Chinese remainder theorem, you can obtain at least one solution modulo this bigger modulus satisfying the system of n linear congruences. Namely, you have to find out your special linear combiners as we have seen in the last slide, right. So, we have to find out this yk which is the multiplicative inverse of your kth submodulus modulo the kth small modulus, and if you do this, then this x will be one of the solutions. If this x that you have obtained as per the Chinese remainder theorem satisfies the condition that it is in the range 0 to m, then well and good. Else you find out an appropriate multiple, or you select an appropriate value of a small l, which will ensure that you obtain a solution in the range of 0 to m minus 1. So, that brings me to the end of today's lecture. Just to summarize, in this lecture we introduced linear congruences, and we discussed two methods of solving the system of linear congruences, one using the extended Euclid's algorithm and another one due to Chinese remainder theorem. Thank you.